The last topic that we are going to talk about in this chapter is the solubility of complex ions. And for right now, a complex ion is really just another way to dissolve partial and insoluble salts and cause them to go into solution. Complex ions are a little bit ahead of what we've been talking about because they involve different kinds of bonding than we have previously discussed. And in the next chapter, we are going to go into how this bonding occurs and a lot more details about complex ions. But really what we're doing now is looking at how complex ions can cause partially soluble salts to go into solution and how they affect our solubility products. So complex ions can be cations or anions, and they're always polyatomic, and they involve a central metal. So usually it's a transition metal, and there are other species bonded to it called ligands. So this bonding between our central metal and our ligand involves a special type of bonding, and then we will talk about that in the next chapter. So here is our complex ion. You can see we put it into an aqueous form because it's going to be soluble. And in this complex ion, iron 2 plus is the central ion and Cn minus is the ligand. So we'll talk about how do we know iron is 2 plus and so forth in the next chapter. Right now we're just talking about the complex ions equilibrium and how they affect solubility products. So the formation of a complex is a specific reaction, and they give it a specific equilibrium constant called K sub F. So to form this complex ion, this is the reaction where iron 2 plus reacts with 6 cyanides to form our complex. And if we want to look at the equilibrium expression for this, it's products divided by reactants. And we need to remember that the 6 in front of the cyanide here gets carried down to our equilibrium expression. And K sub F for this reaction is 1 times 10 to the 37th. And you can see that K sub F is a very large equilibrium. So that means this equilibrium lies very far to the right. So if we put cyanide in solution with Fe2+, it is going to preferably form this complex ion. And we're going to utilize this fact to help insoluble salts that contain Fe2+ to go into solution. And that's what we're going to take a look at right now. One of the most important things you want to remember at this point is that because the complex ion is an ion, because it's charged, it's going to be ionic, so more than likely it's going to be soluble in our aqueous solutions. It's going to go into water. Let's look at an example of how we calculate the solubility of a complex in solution. So here I'm giving you an initial amount of Fe2+ in the form of iron 2 nitrate. Also, I'm giving you an initial amount of cyanide, Cn- in the form of sodium cyanide. We know that these two come together to form a complex given here. And really what we're asking for in this question is, after we form this complex, how much Fe2+ will remain in solution. Here I've given you Kf for our complex, and overall how we're going to do this calculation is by using a method called push forward and trickle back. In the first step we're going to push forward, which means that we're going to assume that this reaction goes all the way to the right, which is pretty safe considering that K sub F is a very large number. The next thing we want to do is calculate our concentration of Fe2+ in our initial solution. We know that we have 0.1 mole of Fe2+ because we have 0.1 mole of iron 2 nitrate. Also, it was given that we're dealing with a 1 liter solution. This gives us a concentration of Fe2+ of 0.1 molar. Then we look at the reaction that goes to form our complex in this situation. And remember, it's a 1:6 to 1 stoichiometric ratio. And we're going to assume that this reaction gets pushed all the way to the right. We have an initial concentration of 0.1 molar of Fe2+, and also we were given an initial concentration of Cn- of 2 molar. Next, we're going to assume all of our Fe2+ is converted into our complex, and in doing that is going to use up a certain amount of Cn-. So we're going to remove 0.1 mole of Fe2+, and because there's a 1-to-1 mole ratio, that means we're going to form 0.1 mole of our complex. between iron 2 plus and cyanide, it's a 1:6 ratio. So if I use up 0.1 molar of Fe2 plus, I use up 0.6 molar of Cn minus. So if we start with 2 molar and we use up 0.6 molar, what we have left is 1.4 molar in solution. This is where we start at, but we can't remain here because we cannot have a zero concentration of Fe2 plus because we are at equilibrium. So now we got to assume some of this will trickle back and form some of our Fe2 plus. So we go ahead and assume that some of this complex will break back up to form Fe2 plus. Now we kind of do the exact opposite. We assume some of our complex is going to break up. In this case, we're going to call it S. It's a 1-to-1 mole ratio. So if we break up S amount of our complex, we're going to form S amount of our Fe2 plus. There's a 1-to-6 mole ratio between our complex and the cyanide anion. If we break up S amount of our complex, we're going to make 6S of our cyanide. Then we look at our equilibrium expression for our complex formation, and we go ahead and plug these numbers into the equilibrium expression for this reaction. So our 0.1 molar minus F, S goes here on top. Fe2 plus is S, that goes right here, and our cyanide is 1.4 plus 6S, that goes right here. And then we go ahead and assume S is small, so we're going to get rid of the S here and the S here, and then we're going to solve for the remaining S using K sub F. So once we remove the S's, we're left with this equation, and we go ahead and do the calculation, and we find out that S is equal to 1.3 times 10 to the minus 39th molar. And in this case, S, we've decided, is equal to the concentration of Fe2 plus. So you can see that the formation of a complex is very effective for removing ions out of solution, and you can tell that because after we form this particular complex, our concentration of Fe2 plus is very, very small. Now let's take a theoretical look at why the formation of a complex can be used to dissolve an insoluble salt. So here we're going to be looking at equilibrium constants and try to come up with an explanation for this. Here's the equilibrium for an insoluble salt, iron 2 sulfide, and here's the Ksp for that insoluble salt. As we already know, iron 2 plus can react with cyanide to form a complex, and the K sub F for that formation of that complex is 1 times 10 to the 37th. Now let's look at what happens when we combine these two reactions together. And in this case, the two reactions can go without any further manipulation. So if I add this reaction to this reaction, I get this third reaction here. And as we already know, for adding in two reactions, the equilibrium constant for the reaction that comes out is going to be the product of the two equilibrium constants of the reactions that we're putting into it. So the equilibrium constant for this reaction is going to be the equilibrium constant, or Ksp, for this reaction times the K sub F for this reaction. And when we do the multiplication, we get that the equilibrium constant for this reaction is 1.2 times 10 to the 26th, which is a fairly large number. Because this equilibrium lies very far to the right, that means if we have, say, our insoluble salt, iron 2 sulfide, in an aqueous solution, so this would be a precipitate at the bottom, if we started adding in Cn minus, what would happen is the Cn minus would cause the iron 2 sulfide to dissolve, and this would form our complex. So we can actually get this iron 2 sulfide to dissolve, even though it's an insoluble salt, and we'll go into solution now. And so overall, we've ended up dissolving this insoluble salt.